Recording underway, and I've done that, so we are all set here. What I want to begin with this morning is a little gift to you, which is a breakdown for test number 1 in terms of the number of items that are going to be drawn from the different major sections that we will complete before we do test 1 just 12 days from today. So the breakdown is there will be 7 questions coming from the introductory material. So those were the light blue slides where we talked about the definition of psychology. We looked at some of the major theories in terms of the great debates in the history of psychology, including nature versus nurture, for example. Then we talked about the subfields. 7 questions coming from there. Last Thursday and then this past Tuesday, we did 2 days on research methods with the red slides. 14 questions will come from that material. And almost half of the questions, 19 out of 40 questions, will be coming from this section on biology and behavior. So certainly you want to keep your head around this material in the biology. That's going to be a major part of what we're doing for test number 1. Okay. I would want to know the names of those. Yeah, I mean, structuralism versus functionalism. Yeah. I don't often ask questions that are like, what was the name of the guy who did X? But I would want to know, behaviorism, for example. That's a pretty important idea. So as we move into this biology and behavior section, what I'm going to give you again is a little advanced organizer outline of how we're going to approach this biology and behavior section. So we're going to begin with the tools of the neuroscientist. We're going to look at what biological psychologists or neuroscientists use to study the brain. We're going to begin with looking at the brains of dead people. Those are going to be called postmortem brain specimens, all the way through some pretty sophisticated brain imaging techniques. So that's the first 20 to 25 minutes or so this morning. Then we will look at the major parts of the brain. So it's basically brain anatomy this morning. Probably about 11 or 12 major structures we will have a chance to review this morning. We'll finish up with that on Tuesday, at which point we will then zoom in. So in the final 10 or 15 minutes on Tuesday when we are face-to-face, we will zoom into the cellular level and look at the neuron as sort of the cellular basis for activity within the brain, okay? I would note that this approach that I'm taking is sort of the opposite of your textbook, which starts at the cellular level and then zooms out. I think it makes a lot more sense for us to begin at a bigger level, looking at the macro major parts of the brain and then zoom in. So for what it's worth, the textbook will actually do these final 2 sections in reverse order, and actually we'll begin the chapter by talking about the cellular components of the brain. I think it makes a lot more sense to start big, as you would looking at a map of a new city you're going to move to, and then zoom in to look at what's going on at the micro level in terms of specific neighborhoods. So let's begin with a review of the major tools of the neuroscientist. We are going to take a look at 5 different major tools together. What I want to do is try to do this in full slideshow mode if I can get some cooperation like I was able to get in the 8 o'clock section. So these are the 5 major tools we're going to take a look at together. Postmortem brain specimens, EEGs or electroencephalograms, PET scans or positron emission tomography, magnetic resonance imaging or MRI, and then finally fMRI, functional magnetic resonance imaging. So when we are done reviewing these 5 major tools in the toolbox of the neuroscientist, what you should be able to do is briefly summarize, like, what is that thing about? So what is an EEG about? How does it work? Not at an incredibly technical level. And probably most importantly, what will it tell me and what won't it tell me? Okay, so there are going to be some limitations for these different techniques that we're going to use. And I need you to be aware of, like, okay, so, a PET scan will do X, but it won't tell me anything about Y. Okay, and I'll explain those advantages and disadvantages, kind of similar to how we talked about the different approaches to research design last week. Okay, so that's how we're going to take a stab at looking at these different tools of the neuroscientist. So let's begin with the post-mortem brain specimens, basically the brains of people who have died, and look at this as our first tool if we are studying the human brain. So what does the post-mortem brain specimen look like? Well, it looks like this. And to orient you to this, what I'll do is tell you that over here on the left side is going to be the front of the brain. If that's the front, then that means over here we're going to have the back. That then means this is going to be the top. And down here where the guy's holding it is going to be the bottom of that brain. Okay, the post-mortem brain specimen. Okay, what does this mean? Well, it's looking at a brain of someone who has died, right? That's what post-mortem means after death. So after death, we look at this brain, and what we get is what's referred to as a gross examination. I'm not trying to be clever there in my wording. It's a gross examination or a rough examination of this brain. It gives me a sense of overall brain structure, what areas might be, malformed, might be bigger than we expect, might be smaller than we expect, etc. Okay. It was a method of study that was especially important maybe 100 and 150 years ago. It's not as important today, but certainly it gives us a really good look at the overall brain structure. And what's obvious here, as you look at this brain, is all this overlying bumpy area is really very, very clear when you take a look at this brain. I'm going to give you a name for that. That overlying bumpy area, sort of nooks and crannies like you'd have on an English muffin. Now I've ruined that for you for the rest of your life, right? Is known as the cerebral cortex. You'll sometimes hear me just call that the cortex. So the overlying cortex is this bumpy outer shell of the brain that surrounds what we're going to call some midbrain structures. Sometimes you'll hear the term subcortical. That just means under the overlying cerebral cortex. So we're going to look at structures like the thalamus and the hypothalamus and the amygdala and the hippocampus and some other structures. Those are all subcortical. What you can see with the post-mortem brain specimen is the overlying cortex, and you can actually see that quite well here. Okay. Obviously, the limitation of the brain specimen approach here, looking at the post-mortem brain specimen, is that the information you get, it can't be used to inform a diagnosis or indicate a treatment because the person's dead. That's obviously a major limitation here. In this brain, this section in here has either been cut out or this person had a really wild kind of brain injury, because that should all look in that area there like the rest of that bumpy cerebral cortex. It doesn't, okay? And if you're wondering what would have been going on, if that was actually damage, I'm not saying that it was because I don't know the whole backstory on this individual, but if that was damaged in that way and looked like that, I'll tell you that there's an area right in here. And I'm not an expert at drawing this stuff or identifying exactly where stuff is, but this area right in here, I will tell you, is known as Wernicke's area. And we're going to come back to this again before we're done this morning, because I've got a slide that talks about these areas of the brain as they relate to language usage. It turns out that Wernicke's area is a part of the brain that's involved with language comprehension. So as you're listening to me right now, one of the areas of your brain that's probably quite active is Wernicke's area. And what I'm telling you here is that this person, if this was actually damage to this brain, would have had a really difficult time understanding what people were saying to them, okay? What's really cool about language is we've got another complementary area of the brain that kind of sits right down in here. Again, I'm not an expert on this brain anatomy stuff, but I'll give it my best shot. This area that I've circled here is known as Broca's area. So let me insert some text up here and tell you that. Broca's area. And rather than being involved in language comprehension, Broca's area is actually the language production center in the brain. Okay? It's the part of the brain that's involved in helping you to produce language, to say things. So right now, as I'm rambling on, my Broca's area is a part of the brain that would be active, right? Because in producing speech, you're moving things. You're moving your mouth and your lips and your tongue and your vocal cords. And it turns out, as we're going to learn this morning, right next to Broca's area, on the back side of this frontal part of the cortex, you've got a strip there that's involved with helping you do movement. Well, that kind of fits, right? It fits in that doing language production is really on some level minimally about movement. We're moving some things around to produce the speech. Okay? All right, so that's the first of the tools in our toolbox here as brain scientists. We can look at the brains of someone who has died and try to figure out what was going on. Maybe we know from before they died they had specific deficits. Well, then we can look at the brain and see if there's corresponding damage areas where we would expect it to be. Okay, so we've got postmortem brain specimens. We've got EEGs. What are EEGs? EEGs, or electroencephalograms, are recording devices that we use to look at electrical activity in the brain. So what we're doing here is we're measuring electrical activity at the level that overlying cerebral cortex. So let's go back for a second. What we're saying here with the EEG is it is going to tell us what's going on at the overlying level of the cerebral cortex here. That's what the EEG is going to provide us information about, okay? Electrical activity at the level of that overlying cerebral cortex, again, that shell. So this is what we're getting with EEGs. There are some things that we're not getting with EEGs. What we're getting is information about electrical activity, basically, if you will, an electrical hum in the brain at the level of the overlying cerebral cortex, okay? What we're not getting, before I forget to say so, is any kind of brain image, right? Look at what we're getting on the computer monitor here. Does that look like a brain? No, all we're doing with this is recording via these electrodes that are connected to the person's forehead and edge of their scalp and around their head. We're getting a measure of what's going on at that overlying surface. We're not getting an image. And also what we're not getting with an EEG, another limitation would be it's not going to give us any information about underlying, also known as subcortical brain areas, right? So if your question as a researcher or as a clinician is about underlying brain areas, the EEG is not really the ideal tool for you. The EEG wave patterns that you see depicted over here on the left side on the computer monitor correspond to different states of consciousness. So we are going to have a whole chapter in part 2 of our course. After we do sensation and perception after test 1, we have a chapter on consciousness. And in that chapter, we'll talk about how the brain waves of a person who is awake and alert differ from the brain waves of someone who is in deep sleep. So when you are awake and alert, the brain waves kind of look something like this, okay? And I'll contrast them in a second with the brain waves of someone who's in deep sleep. In deep sleep, 2, 3, 4 o'clock in the morning, here's what your brainwave tracings likely look like, okay? What's the difference here? Well, the difference is technically what we call this height of the wave is the amplitude of the wave from the top to the bottom. Obviously, when you're in deep sleep, right down the bottom here, deep sleep is characterized by large amplitude brain waves when we look at the EEG output on the monitor, right? Versus when you are awake and alert, there are these small amplitude, relatively higher frequency brainwaves. Okay, so we'll get into some of that in the section on consciousness. Another use for EEGs could be in helping to diagnose and monitor seizure disorders like epilepsy. But again, only at the level of the cortex are you getting any information. If you're wondering about some of the underlying or subcortical brain structures we're going to talk about, the EEG is not going to give you information about those underlying areas. Okay. All right, hold on one second. Saying something about audio. Let me mute myself and then unmute myself. All right, I'm back. Tell me if that's okay. Okay, that must be your internet connection. Obviously, the ideal situation for your internet connection is that you're hardwired in, and that's what I'm doing on the Mac that I'm that I'm connected in with. If you are sitting somewhere where you're on some semi-wonky wireless connection, you know, it's going to go in and out like that sometimes. Okay, so we've got the post-mortem brain specimen, the EEG, the first two of our 5 tools in our toolbox as neuroscientists. What's number 3? Number 3 is when we finally get into looking at brain imaging. So let's take a look at some of the brain images we can get by doing something called a PET scan. So let me run through the elements here of a PET scan. What's involved here? Well, PET scan involves injecting you in your arm, right, like you would to draw blood or whatever, with a tiny harmless amount of radioactively tagged glucose. Interesting. What's this all about? Well, it's radioactively tagged effectively so we can trace it. It's like putting a little GPS tracer on this harmless amount. Yeah, I like the harmless. Radioactive and harmless. Okay. The glucose is the fuel that your brain uses as you're doing different activities. So the logic here is follow the fuel, see geographically, if you will, in the brain where that fuel gets burned up, and that will tell me something about what aspects of functioning that part of the brain is involved with. You get the idea here, right? Follow the fuel, where the fuel gets metabolized, where it gets burned up. That tells you as you're reading a book or you're listening to music or you're looking at a beautiful picture or you're remembering what you had for dinner last night, what parts of your brain are lighting up as you do those different activities tells you something about the role that they play in your everyday functioning. Active areas in the brain light up in reds and oranges and yellows. Less active areas light up in blue. So I think of these as sort of hot colors versus cool colors, right? Reds and oranges being the hot colors, blues and greens being the cool colors. It gives us information about brain function. What it doesn't really give us so much is a really pretty look at brain structure. So we're going to get information here about what's going on in the brain in terms of functioning, what's active as we do different activities. Not so much about brain structure, okay? So let's take a look at what we actually get here in terms of outputs. So this is a brain imaging technique. So one way in which a PET scan is different from something like an EEG is an EEG does not give you a picture of the brain, whereas a PET scan does. So we're looking at different types of auditory stimulation here with this graphic from the UCLA School of Medicine. The orientation here for you guys, just so you know where things are, is that this is the front of the brain here. Well, that's the front, and that must mean that this is the back. This over here would be the left hemisphere, and this over here would be the right hemisphere. Right, and that's true in all 4 quadrants. So in each of these quadrants, the orientation is the same. What we're getting here is a sort of Goodyear blimp view down into the brain. We basically have told the computer, effectively slice off the top of the brain, pull it off, and let me look down in there. It's called a horizontal view down into the brain. What we have, in terms of the logic here, is a baseline resting state in the upper left side. Okay, so you're in this PET scan machine and you're taking just your time getting oriented to the task. And then we have you do different auditory stimulation tasks. You're listening to language, you're listening to music, or maybe you're listening to spoken words with music playing in the background. And what I want you to notice, again, in terms of the logic here, the active areas are the reds and the oranges. So when we look at these other 3 quadrants, after we take out the baseline information here, let's see what becomes more active. What gets more active as you take a look here at listening to language? Maybe you're listening to someone read an audiobook kind of scenario. Well, reds and oranges and yellows are indicating more active. What's becoming more active, first of all? Left side or right side as you're listening to language? Yeah. Language is on the left, so I'm going to put left L equals language, and we're going to come back to that when we have a discussion on Tuesday about split brain patients, because when you can't share language information back and forth between your 2 hemispheres, which is the case with split brain patients, some really interesting things occur. As you're listening to music, what areas become more active? looks like it's right hemisphere, right? So over here with music, listening, hearing a song, whether it's classical music or someone singing something, you've got right side activation because we can see these areas here lighting up. Obviously, there's some frontal lobe activation and some rear of the brain activation as well. But in terms of left versus right, it looks like language is more left, music is more right. And this upper right side might be someone reading a speech with, you know, dramatic music playing in the background. We've got a little bit of both sides going on there in terms of what's getting active. So again, a really nice look at brain function, right? What's going on in terms of brain activity, okay? Not such a beautiful picture of brain structure. I'm going to show you some beautiful pictures of brain structure on the last two slides about the tools that neuroscientists use. But in terms of functioning, and what areas are firing up, if you will, as you do different activities. A PET scan does a really nice job of that. Okay. All right, let me stop there for a second. So, any questions across either postmortem brain specimens, EEGs, or PET scans? Cool. Tool number 4. Want to get a beautiful picture of brain structure? Check this out. We're going to take a look at our MRI slide here. Look at that. That is awesome, right? What we have here is what's called a sagittal view, which in English means you split the brain into left and right halves. So sort of a split down the midline here. In the middle, we can see right here, actually, this band of fibers that we're going to talk more about together on Tuesday. It's called the corpus callosum. That's actually the bridge that connects the left hemisphere with the right hemisphere. Here is all that overlying cortex. We saw this on the postmortem brain specimen. We could see it really nicely here in the MRI. So we've got the frontal lobe. We'll talk about the parietal lobe, the occipital lobe, and then the overlying temporal lobe we can't see because we've sliced into sort of the midbrain area. We can see the thalamus and the hypothalamus and some of the limbic system structures in here, and the medulla down in here, and the pons. There's a piece of cauliflower. There's a lot of good stuff here. The piece of cauliflower is the cerebellum. Okay, so what does the MRI stands for? Magnetic resonance imaging. It uses magnetic fields and radio waves. You don't need to get all wound up about exactly how this works technically. What I want you to understand as a big take-home message is it gives us a really good look at brain structure. It doesn't give us any kind of functional information. Okay, so not any functional information from doing just a regular old MRI. Okay. So the picture now at this point would be PET scan, functional information, MRI, structural information. Is there a way to sort of get the best of both worlds, sort of have your cake and eat it too, and see both the underlying structure as well as the functioning of those different structures? It turns out that there is a way to get all that, and the way that you get all that is you do an fMRI, which has this crazy acronym of lowercase m, and then capital MRI. I don't know why it is that way. But this is the technique that combines the benefits of both the PET scan and the MRI. And it does so by giving us both structural and functional information, right? Information about both brain structure and brain function. So you don't have to choose what you want to get here when you do an fMRI. We're going to get both. Here's the coolest thing about this fMRI picture. I don't know if any of my other SI leaders are here, but one of our SI leaders is Shyla. She's the one that said, my name begins with an X. When you look at the schedule up there, you're never going to find me. Shyla has been involved in a brain imaging study up at UCSD during her time here at SDSU, and she had an fMRI picture, and she's like, I'm going to send this to you, and if you want to use it on the slide where you talk about fMRIs, go right ahead. So we are seeing areas lighting up as she's doing some kind of activity. I don't know exactly what they had her doing. In the back of the brain here, you can see that really nice look at Shyla's cerebellum there. Really kind of cool. This is going to be, again, some of those midbrain subcortical structures. Here is Shyla's corpus callosum, this white strip here. Again, that's going to be connecting the two hemispheres of the brain. So this is another sagittal view where you basically, tell the computer to slice it down the middle and show me what it would look like if I slice it down the middle, and in this case, pulled out the left side of Shiloh's brain and let me look in here. Okay. Shiloh's been doing this up at UCSD, so if you're wondering where this kind of stuff goes on, they've got some brain imaging stuff that they do up there. All right, so that covers everything on these 5 major tools in the toolbox of the neuroscientist. I want to show you guys this nice summary from your textbook, Infographic 2.3. On the left side over here, what we get is a nice look at tools that will let you look at brain structure. So I didn't talk about CAT scans, but you can read about them. So I've mentioned already earlier in the course where I may not cover everything, and your job is to sort of pick up the ball and run with it to read about CAT scans in this case. MRIs, looking at brain function. There's an EEG, right? No brain image. Nothing about subcortical structures. PET scans, awesome information about brain function, but not great pictures of structure. fMRI, best of both worlds, right? Combining the advantages of both the MRI and the PET scan to give me both structural and functional information. Okay? Any questions on any of those techniques before we turn the page and get ready to look at some of the major structures in the brain? All right, before I do that, let's do a little polling question. What I want to do with the polling question is have you give me an answer, but when you give me your answer, tell me why you think that is the answer. So I want to have you dig a little more deeply and help your classmates learn how to get these questions right in terms of how you explain your answers, right? I think it's really helpful to say, I think the answer choice is B and here's why. Okay, so let's take a look at the first of, I think I'm going to end up doing probably 3 different polling questions with you guys today. So, Sophie had a bad fall while snowboarding. After being rushed to the hospital, she underwent a brain imaging technique where still pictures of her brain were taken. Although everything appeared to be intact, her doctors were still unsure if her brain functioning was normal. Okay, what did they do with her? Did they do an EEG, a PET scan, or an fMRI? Tell me what you think and then explain to me why you think that. All right. Okay, MRI shows brain structure and not function. Okay, why is it not an EEG? How can we eliminate choice A? What do we know? Yeah, the EEG doesn't give you a picture, and it says in the question it's an EEG, it's a brain imaging technique, right? So it's not EEG. And because we don't know about, it says unsure if her brain functioning was normal, anything functional then goes, right? So basically by process of elimination, I could say it's not this because it's an imaging technique. Because they're unsure about her brain functioning, it can't be anything that's functional. So we're basically left with MRI. So again, if you can use a process of elimination like that, even just to get it down to 2 choices or maybe 3 choices instead of 4, you start tipping the balance in your favor in terms of getting more of these multiple choice questions right. Okay? Alrighty. So now we are going to embark on an admittedly sort of rote review of major brain structures, right? Little brain anatomy mini lecture for probably the next 40-ish minutes. So I don't really know any other more creative ways to go through. Here's the part and here's what it's in charge of than to do just that. So we're going to run through this together. And I'll try to give you some ways to remember some of these things, some little tips and tricks and techniques to try to keep track of all this brain anatomy. So we're going to begin at the base of the brain in an area that's often referred to as the brain stem. So we've got this young woman here who's got a nice semi-transparent skull. So coming up from her spinal cord, the very first structure that we encounter down in here is known as the medulla. And what I'm going to do is just number these for you as we go through them. So the medulla number 1 is the structure that I'm going to refer to as the life support system for you in terms of brain structures, right? So this is basic life support because it plays an important role in vital body functions such as heart rate, breathing, blood pressure, and blood circulation. Heart rate, breathing, blood pressure, and blood circulation. Okay, that's important, right? I mean, I usually say at this point, there are no unimportant parts of the brain, but without the medulla, what happens? If you damage your medulla, what is the pretty much immediate result? Yeah, you're going to end up dead. This is what keeps you alive. The good news is you've got this located in a place where you're not going to like trip on a crack in the pavement, fall, bang the front of your head and end up dead because you damaged the medulla, right? It's buried in here. Basically, if you wanted to connect the dots and point to where it is for yourself, it's in and up through the back of the roof of your mouth and then in and up from the base of your skull. If you could sort of push your fingers together, where they meet is pretty darn close to where the medulla is, okay? In conjunction with the pons, the medulla is referred to as the brain stem. Why? Well, because it kind of looks like a stem. It kind of looks like a stalk, right? So extending up from the spinal cord, we begin with the medulla. Next up is the pons. Pons actually is the Latin word for bridge, okay? So it's a Latin word for bridge, and that's a good summary of what the pons does in terms of brain functioning. What it does is it relays or serves as a bridge for information, nerve impulses basically being exchanged between higher and lower levels of your nervous system. So we could see it right in here, the pons. And what I'm saying is that information is going through the pons from down below to the overlying cortex. So we're seeing messages heading in that direction. And there are messages coming from above being sent down below from the overlying cortical areas, and that information is getting routed through the pons as well. So when I think of pons, I think of bridge, because that's actually what the word means in Latin, okay? It also contains neurons that help regulate sleep and neurons that are involved in dreaming. So the pons has a connection with sleep and dreams as well. We will cover that briefly in the section on consciousness when we talk about the biological account for why we dream. And basically that account boils down to a suggestion that the pons is firing random neural messages up to the overlying cortex while you're sleeping. And basically to account for that random neural firing, what the overlying pretty sophisticated cortex does is it sort of makes up a story to account for this hum or this buzz, if you will, that's coming up from down below in the pons, okay? I'm going to save the medulla for a second. The medulla, I'm sorry, we did the medulla and the pons. I'm going to save the thalamus is what I'm trying to say for a second, because I've got built into the next slide another structure that's pretty darn close geographically here within your brain to the medulla and the pons. And that structure is known as the cerebellum. So let me get rid of my scribbling here. And you might be wondering, why do you have a picture of David Beckham when you are talking about the cerebellum? Because it turns out that the cerebellum is involved and concerned primarily with muscle movement, coordination, and balance. Let me just type those down the bottom here, right? Muscle movement, coordination, and balance. Well, I guess if I didn't want to have a soccer player, I could have a dancer, I could have a figure skater, I could have a gymnast, because they are all people who have really good skills in terms of muscle movement, coordination, and balance. Kristen's going to remember the cerebellum as the cerebellum, apparently. Whatever helps you, that's fine. Okay. What I would mention here as well, so cerebellum, if I continue numbering, I guess we had medulla, pons, cerebellum would be number 3, right? The cerebellum, I mentioned this in passing on Tuesday, when we were talking about that alcohol study, right? 0, 2, or 4 ounces of alcohol and looked at how it affected your physical coordination skills? Yeah. Okay. So the cerebellum, it turns out, is one of the first structures that is negatively impacted by alcohol. So what do they make you do if you are stopped at a field sobriety checkpoint? They make you do things that are about muscle movement, coordination, and balance. So the logic here is this. If you've been drinking, it's going to negatively affect your cerebellum. The cerebellum is in charge of muscle movement, coordination, and balance. So I'll ask you to do things like walk in a straight line, heel to toe, like stand on one foot, like close your eyes and bring your arms in and touch your nose with your index finger. All those things in terms of those behaviors are about muscle movement, coordination, and balance. If you can't do them, your cerebellum presumably is not working right. If your cerebellum is not working right, it could be because of alcohol intake, okay? And especially if you reek of alcohol, it doesn't take Sherlock Holmes to figure out that, drinking is probably what's responsible for the fact that you're stumbling around, right? So if you've ever seen people stumbling around or falling down after drinking alcohol, it's because their cerebellar functioning has been screwed up by the alcohol intake, okay? Any questions about the cerebellum? That's a pretty dated picture. I'm going to have to come up with something new because he hasn't played for the Galaxy at all. Down the bottom there, muscle movement, coordination, and balance. I scribbled it in down the bottom of the slide right there. Okay? All right. Let's go back to that previous slide and do the thalamus, I guess, is number 4 here. So we had medulla number 1, pons number 2, cerebellum number 3, and now the thalamus is going to be the relay center, he said, for sensory information, okay, other than smell, okay. Smell, it turns out, gets routed in a slightly different way, and I am going to say that the thalamus is analogous to O'Hare Airport in Chicago. And now you're going to be like, dude, what the hell are you talking about? How is part of the brain like O'Hare Airport? Well, here's the idea. Visual information, for example, is coming in through your eyes. It's going to get routed through the thalamus here, and it's ultimately going to get routed to the back of your head here in this area called your primary visual cortex and the occipital lobe in the back of your head. Okay? Well, I'm saying that this thalamus structure in here is like O'Hare Airport because if you are traveling from either of the coasts, the East Coast or the West Coast, to some mid-size or maybe even smallish town in the middle of the country, it's very likely that the airline route to get to that smaller city is going to be through O'Hare, right? So I have a brother who lives in somewhere in Illinois called Jacksonville, Illinois. If you fly to visit my brother in Jacksonville, you're probably going to get routed, if you're coming from Philadelphia, where I grew up, through Chicago to Jacksonville. If you're coming from San Diego, probably through Chicago to Jacksonville. Well, in a similar way, everything other than smell, which has a slightly different, more direct route, gets pushed through the thalamus at some point. It's like a switching center or a hub, if the word hub helps you, right? So auditory information will come in through your ears, it will go through the thalamus, and then ultimately it will get distributed out to the temporal lobes, which kind of wrap around your brain and sit in and up from where your ears are, okay? So again, the thalamus is a relay center for sensory information, okay? Let me stop there for a second. Any questions about that? We're going to come back to that a couple times. So keep that in mind because we have a whole section on sensation and perception right after test number 1. And we'll even talk about the thalamus when we get to the section on schizophrenia, one of the psychological disorders where you see things and hear things that aren't present. Okay. Turns out that people with schizophrenia have a thalamus that's smaller than we would expect and a thalamus that is less metabolically active than we would expect. And what do? They get false sensory experiences that we call hallucinations. Okay, so that's the deal there in terms of what the thalamus is involved with. Cerebellum in this picture is down in here. It's a little bit hard to see right there. Okay, That's why I got the next slide, because it's a little bit of a better look at that. All right, so let's meander on in this earth-shattering review of brain anatomy. We're going to talk about the limbic system, and I'm going to help you remember the limbic system by giving you the word ha. Why am I saying ha? Well, because it's got three structures, and they begin with H, A, and H. So here's the thalamus, which we already talked about. It's not actually pink, but they're giving you some colors here to help you. Here's the hypothalamus. The hypothalamus sits under the thalamus. That's why it's called the hypothalamus. So this is the first H in ha for the limbic system. And the hypothalamus is involved in tons of regulated behaviors. So I guess if I'm still numbering things, this is number 5, right? What kinds of regulated behaviors is it involved in? Well, regulating hunger, thirst, body temperature, blood pressure, heart rate, and to keep it clean, I'll call them reproductive behaviors. Basically, sex drive is regulated by the hypothalamus. Man, that's a lot of stuff that matters, right? Eating, drinking, body temperature, et cetera, right? Hypothalamus is in charge of regulating all these things. In addition to that, if that's not enough, and now I just realized I forgot to say this to the 8 o'clock section, it is also in control of the pituitary gland. Controls the pituitary gland, which is itself the master gland of the endocrine system. So this is crazy, right? We've got something that's in charge of the endocrine system, which is basically your hormonal system, and it has something in charge of it. And well, the thing that's in charge of the thing that's in charge is the hypothalamus. So the hypothalamus in charge of the pituitary gland, which is in charge of the hormone secretion system here. Okay. So, wow. I mean, that's, again, no unimportant parts of the brain, but that is pretty darn important. Okay. All of those different things. I would mention here, because I've got something here about, body temperature and blood pressure. You might look at your notes and say, oh, I thought you said that the medulla was in charge of that stuff. I did. It turns out that different aspects of our functioning can be regulated by different parts of the brain. So we talked about the cerebellum as muscle movement, coordination, and balance. Well, we've got a strip of the overlying cerebral cortex that plays a really important role in terms of movement. So there are networks. I think that's the thing I want you to understand here. There are networks that help control different aspects of our functioning. It's not one isolated structure doing its own thing. Okay? These things are connected together and they work together. When you teach it, you sort of have to break it up and go one piece at a time, but the reality is that these things are integrated with each other. Okay? So hypothalamus is the first H in ha. Amygdala is the A in ha. The amygdala regulates emotion and aggression. So let me carry on with the numbering, right? So this is going to regulate emotion and aggression with a primary focus, honestly, on fear and anger. And I would, if you made me pick one thing to remember about the amygdala, I would focus in on the fear part, okay? Because we're going to come back to this a couple times in our course when we talk about phobias, we talk about emotion, stress, and health, and sort of immediate reactions to stimuli around us. The amygdala, in my mind, is it's like a stamp, right? You have one of these things you can stamp a paper and put a star on it or whatever, and you pop it on the ink pad and then you bang it on the piece of paper. Well, the amygdala basically stamps certain emotionally salient events. That means emotionally significant events as things not to be forgotten. They could be scary, horrifying events like the 9/11 terror attacks. They could be happy, joyful events like your sister's wedding or your high school graduation or whatever the case might be. The amygdala basically stamps those things and says, hold on to this one. This one means something emotionally, right? This matters. And in conjunction with the final structure here, it's probably going to be what helps you to remember these things. So the hippocampus, finally here, is basically the save button for memory. Okay, that's how I think about the hippocampus, is it is effectively the save button for memory. Okay, without a fully intact and functioning hippocampus, you are not going to be able to take information from short-term memory and save it over onto the long-term memory hard drive, right? This is the problem. If you wanted me to diagnose Dory, this is the problem for Dory. She is constantly living in the present moment because she doesn't have a hippocampus that lets her hold on to whatever is going on in the present moment. So if you get minutes or hours out, she won't recall interactions that you had previously, right? She tells, she tells Nemo's dad, she tells Marlin, I've seen the boat, I can show you where it is. And then Marlin starts following her to the boat, and she turns around and is like, why are you following me? She doesn't remember what just went on, right? Just moments before. So the hippocampus, again, sort of the save button for memory, okay? Is the amygdala something that also holds on to the trauma? Yeah, what I'd say is this is, if we had you plugged into a PET scan machine or an fMRI, this is what would light up. If you experience some traumatic event, and it could be sights or sounds or smells or news reports related to that traumatic event, if I exposed you to those stimuli, your amygdala would be firing up and lighting up very, very quickly in those brain imaging machines. Does that make sense? So if you were a soldier with combat experience, and I did something like, showed you scenes from some, horrific battle in a war movie, that's going to be firing up and really making that amygdala active as you're seeing those things and basically being triggered by those stimuli. Okay? All right, that's a lot. Let me be quiet for a second. Questions on the limbic system or the thalamus, or going back to the medulla, the pons, the cerebellum. I wouldn't say the amygdala triggers PTSD. What I'd say is, if you made me guess what parts of the brain play a role in PTSD, post-traumatic stress disorder, the amygdala would be at the top of my list, right? That's where we'd see activation. And if we wanted to intervene in some way, if you wanted to develop some magic pill that is going to help with, no longer being traumatized by those traumatic events and those memories, that pill should probably do something related to the amygdala. I'm not saying there is such a pill, but that's the logic here. All right, let me ask you another clicker question because I'm tired of talking. And again, give me an answer, but also give me an explanation for this one. Saw Kristen and Amanda and Maria and so forth. Yeah, that's the medulla, right? Why the medulla? Because the medulla, we said, is basically the life support system that's built into the brain, right? Keeps you alive. Without it, well, then you're dead. Okay, good. So let's take a step back for a second and sort of see where we're at and then where we're going to head in our last 20 to 25 minutes here. So I've got a slide that sort of gives us an overview of the big picture here. So we talked about medulla, pons, and cerebellum. I don't see the pons on here, but here's the medulla, right? Controls heartbeat and breathing, keeps you alive. Cerebellum, voluntary movement, balance. Okay, cool. Medulla, pons, cerebellum. We did thalamus. There it is, relay center between lower and higher centers. Sensory information. I called it like O'Hare Airport. The little purple boxes are the 3 HA structures in the limbic system. Hypothalamus, basically regulating just about everything. Amygdala with emotion, and hippocampus with memory. So hypothalamus, amygdala, hippocampus. On Tuesday, we're going to talk more about this corpus callosum structure, We saw it a little bit in the MRI slide. It is the band of fibers that serves as a bridge between the two hemispheres. It lets you take information that might have landed in the right hemisphere and slide it over to share it with the left hemisphere. Okay, so that's what the corpus callosum is going to be about. We're going to say more about that on Tuesday. I want to turn our attention now to the overlying cerebral cortex, the ultimate control and information processing center. Going back to the postmortem brain specimen slide, this is what we saw, that overlying shell, or the bark, if you will, that is wrapped around these subcortical and midbrain structures, things like the thalamus and the hypothalamus and hippocampus and medulla and all that. Okay, wrapped on top of all that, we have this overlying cerebral cortex, which is the part of the brain that is noticeably different in humans versus the brains of other species. So if you look at humans versus dogs versus cats or rats or mice or monkeys or whatever, the cortex is much, much bigger in humans. And then the specific part of the cortex that is gigantic in humans versus those other animals is the frontal lobe. Okay, so we're going to talk about these 4 lobes of the cortex. By the time we're done, you should be able to identify where they are. If I gave you a diagram, you should be able to know what I'm pointing at. And you should know what major aspects of functioning they're involved with. We're going to spend the most time on the frontal lobe. Okay? Turns out that the frontal lobe, again, is the part of the cortex that is just gigantic in humans versus other species. We'll talk about the parietal lobe here. So if you're moving from front to back, sort of over the top of your head, this is, sort of the middle of the top of your head. We've got the parietal lobe. You get to the back of your head, you've got this occipital lobe, which we have already mentioned is involved with vision, right? So I said visual information comes in through your eyes, gets routed through your thalamus, and ultimately back here to the occipital lobe in the back of your head. And then the temporal lobes, you've got one on the left side and one on the right side. These are involved with hearing and language comprehension. We'll say more about that in a bit. They sort of wrap around the sides, almost like an ear flap on a football helmet, something like that. I want to identify 4 major aspects of functioning that the frontal lobe is involved with. And then after laying them out for you, we'll spend some time talking about them. I'm going to tell you, we'll spend almost 10 minutes talking about the frontal lobe, and then we'll spend just a couple of minutes, a minute or 2 on each of the other 3 lobes. Okay, lots of time on the frontal lobe because it's in many ways the star of the show here. So what is the frontal lobe involved with? Well, the frontal lobe is regarded as the seat of intelligence, reasoning, and abstract thinking. So intelligence, reasoning, and abstract thinking. So if you want to find where those higher level human abilities are, right? Being able to logically reason through some scenario, being able to think about things that are not present, being able to entertain hypothetical scenarios. That's all frontal lobe functioning, okay? That's number 1. Number 2, the frontal lobe helps to control movement. Okay, we're going to talk about the primary motor cortex, basically a strip along the back side of this frontal lobe that helps to control movement of your body. More on that in a minute. The frontal lobe also possesses what we refer to as executive control. This is what helps you plan out and then execute, hence the name, right? A series of steps to complete some task. I'll come back and say more about that. The 4th and final aspect of functioning that I want you to know that the frontal lobe is involved with is in terms of inhibiting inappropriate responses. So inhibits inappropriate responses. I'm going to just compare this to the brakes on the car. Okay, this is what helps you keep yourself from being overly impulsive. It's what helps you think through things so as not to do something that is maybe dangerous to yourself or others. More on that in a bit. Okay, so let's review these together. Intelligence, okay, reasoning, abstract thinking. Okay, intelligence, reasoning, and abstract thinking. So again, doing higher level stuff, right? Comparing and contrasting two different cultures and the beliefs that they have about the role of women. That's higher level stuff, right? Analyzing some physics problem and being able to explain to someone how things would work in a new scenario. That's frontal lobe functioning, intelligence, reasoning, and abstract thinking, okay? Controlling movement. This is where I want to start digging in a little bit. This strip right here on the back side of the frontal lobe that I'm pointing at is known as the primary somatosensory cortex. So I'll draw some ziggy-zaggy lines here, right? The primary motor cortex. I often will refer to it as the motor strip. It is in charge of, well, movement. That's what motor is about, right? Moving things. I want to tell you two things about this motor strip, which you can see down below here in light blue. Here it is in the left hemisphere. Here it is in the right hemisphere. That primary motor cortex, or this motor strip. Two things about it. Number one, it is something that shows evidence of contralateral control. And number two, it obeys what I refer to as the proportionality principle. And that's what's depicted up above. I'll get to that in just a minute. Okay, so contralateral control and proportionality principle are two ideas that I want you to hold on to related to this primary motor cortex, again, the motor strip at the back of the frontal lobe. What does contralateral control mean? Anybody ever heard that phrase before? If I'm waving my right arm up and down, and my shoulder is popping as I'm doing that, which hemisphere in my brain is controlling the movement of my right arm? Omar's got it, right? Left side. So the left hemisphere controls right side body movement. Conversely, the right hemisphere controls left side body movement. So there's contralateral control in terms of movement. There is also this proportionality principle. This is where it gets a little bit more slippery. This weird figure up above here is showing you that there is proportionally more brain space dedicated to parts of our body that we can move in more complex ways, okay? Basically, the rule of thumb is if there's a body part that you can move in really complex ways, like your hands and your fingers and your thumb, give that part of the body more space in your head, more brain volume dedicated to it. And if there are other parts that you can't really move in very, very complicated ways, like your trunk or your hip, then only give them a small slice here. Does that make sense? Bigger slices in the brain for parts of the body where you can do more complex movements. Does that make sense? So these two things are holding true here for the motor strip. And in a couple of minutes, when we come back to this slide, the same two principles are going to apply to the strip that is in charge of the sense of touch. We'll come back to that in just a couple of minutes. Okay, let's go back to the previous slide and talk a little bit more about the frontal lobe. So we've got intelligence, reasoning, and abstract thinking. We've got movement with that contralateral control and proportionally more space here in the cortex for parts where you can do more complex movements. Number three, I said, is executive control. Again, this is the ability to plan out and execute a series of steps that is required to complete some task, right? So to complete your task of getting prepared for this course, you needed to register for it. You needed to find out what the books were going to be. You need to go get your course materials. You needed to know how to log into Blackboard and so forth, right? If you're going to bake a cake for your brother's birthday today, and you have to get the ingredients, you've got to make a list of ingredients. You got to go to the store and buy those ingredients. You got to come home and follow the recipe and combine those ingredients in the correct way. All of those are examples of this executive control, right? It's higher level stuff. Executive like a CEO, right? Chief Executive Officer, the person who's kind of in charge and helps plan out where the business is going. So the frontal lobe in some ways is sort of like the CEO for the brain, okay? The fourth part of this list of functions of the frontal lobe is in terms of inhibiting inappropriate responses. Hannah said, is that limiting impulses? Yeah, that's the idea, right? Keeping you from yelling fire in a movie theater, assuming that there is no fire. Keeping you from saying the word bomb anywhere near an airport, okay? Keeping you from blurting out in class, this is the most boring lecture ever, or blurting out in church, this is the most boring homily ever, right? Saying to your friend, your haircut is hideous, okay? Even if it is, we try to keep ourselves from doing those things. Here's a really cool thing about the frontal lobe. It is the part of the brain that takes the longest to mature. It continues to develop and mature into your mid-20s, okay? It is not fully mature in teenagers, okay? So does this explain why teenagers might do some impulsive things? Yes. Do teenagers sometimes act without thinking? Yes. Impulsivity, right? That's the idea here. Brakes on the car, keeping you from doing impulsive things. Now, if you start thinking about impulsivity and you think about something like attention deficit hyperactivity disorder, right? ADHD. Kids with ADHD, what they do is a lot of acting without thinking, right? And they're clumsy and they injure themselves and they injure other kids and they end up in the ER a lot more than non-ADHD kids. You might think, hey, I wonder if that ADHD thing is somehow connected with frontal lobe functioning. It is. It's under arousal. It's under activity of this frontal lobe that can contribute to not only those problems with impulsivity, but also some problems with attention, right? And sustaining tasks, right? And being easily distractible. That turns out to be something that we see with ADHD, which is another part of what goes on here in terms of frontal lobe functioning. Tourette's could be connected with frontal lobe function. It could be related to other things as well. I'm not going to get into other details of that. If you're having problems with sound, it's got to be your internet connection. The good news is everything's recorded. You can go back into the recording, and if you've got a good, reliable internet connection, it's not going to be jumping out. Okay? All right. Parietal lobe. I'm going to make this really, really simple. Parietal lobe is about your sense of touch. Okay? Sense of touch is parietal lobe, and it's this strip in particular. We're going to talk about what we're going to call the primary somatosensory strip. So I'm going to color it over here in blue. Sits adjacent to that primary motor cortex strip at the back of the frontal lobe, here at the front of the parietal lobe. Okay? The front of the parietal lobe is this primary somatosensory strip. Okay? It's got the same principles connected to it that we had before, right? We're going to talk about on the next slide here then contralateral control and proportionality. So if I were to stroke the palm of your right hand with a feather and you had your eyes closed, when I'm stroking the palm of your right hand, it's left hemisphere activity that is going to be seen. Conversely, if I stroke the palm of your left hand with a feather, we'd see right hemisphere activity, again in this primary somatosensory strip at the front of the parietal lobe. Okay. All right. If it's a bunch of people, it could be the network. I mean, I'm not in charge of the SDSU wireless network. So if it goes out, go back into the recording, you'll be in just fine shape. So contralateral control and the proportionality principle. Proportionally more brain space dedicated to parts of your body where you're more sensitive to touch. Okay? Without getting too graphic here, right? You have more brain space dedicated to your hands, to your face, to other parts of your body, because that's where you're more sensitive to touch. Here's the forearm. It's this tiny little sliver, right? Because no one's like, oh, I wish you would touch me on my forearm. It's not where you're particularly sensitive to touch. So again, less brain volume dedicated to that spot. That's the proportionality principle as it relates to the somatosensory cortex. Okay, we'll talk about olfactory stuff. We'll talk about smell in the section on sensation that comes after test number 1. All right. let's go back to that previous slide here. So we've taken care of the frontal lobe, the parietal lobe, the occipital lobe. We can keep this really simple and say the occipital lobe is about vision. Okay, processing of vision, instead of visual formation, say visual information. So to make this really clear, I'll just say this is vision, right? So in the back of the head here, as crazy as that sounds, that's where we process visual information, okay? So that information comes in through the eyes, gets routed through the thalamus, back here. So the occipital lobe is what receives information from the eyes and analyzes that information to give a sight. You can see stars if you bang the back of your head, if you fall down and bang the back of your head, or if someone hits you in the back of the head during a football game or a soccer match. If you damage this visual cortex here in the occipital lobe, you can end up with what's called cortical blindness. So you can get partial or complete blindness as a function of damage to this occipital lobe. So that's vision. So parietal lobe is touch, occipital lobe is vision. If I keep this really simple, temporal lobe is about hearing, okay? Hearing and then language comprehension. I'll say more about language comprehension in just a minute. Okay, so the temporal lobe, again, you've got two of these. This is the left temporal lobe that we can see here. If in your mind you picture the other side, the right hemisphere of the brain, there would be a sort of mirror image right hemisphere temporal lobe as well, again, for processing auditory information. That information is going to come in through your ears, get routed through the thalamus right in the middle of your head, and then that information gets dumped back out to these auditory processing areas in the temporal lobes. Okay. Yeah, if you hit the back of your head especially, it's almost like you're manually stimulating this visual cortex in your occipital lobe. Yeah. Cool. It's a good point, Ryan. Eduroam is supposed to be the future here for the wireless stuff at SDSU, but I don't want to get involved in spending tons of time talking about that stuff. All right, couple final points here regarding lobes of the cortex. The frontal lobe information that I shared with you guys, especially this point here about inhibiting inappropriate responses, we came to know a lot of that stuff because of the famous case study of Phineas Gage. I mentioned his case study last week when we were talking about, well, case studies as an approach to descriptive research designs. He was working on the railroad all the livelong day. There was a metal tamping iron, there was some gunpowder, there was a spark, and then there was a blasting of this tamping iron pole basically through his skull, through his left cheek, out the top of his skull, thereby damaging pretty dramatically his frontal lobe. I mentioned this last week, but his doctor then said Gage was no longer Gage. He became this mean, nasty, inconsiderate, sort of irascible guy who would say or do whatever came to mind. He wouldn't ever edit. He wouldn't ever inhibit impulses. His personality basically really changed. And that was an indicator that the frontal lobe would probably be a driver of some of those things than, that we're seeing change so dramatically in him. What else do I have for you here? I've got one more slide I want to show you regarding these lobes of the cortex. It's this one, just to give you a good look at visual and auditory cortex areas. So there's a visual cortex both in the left hemisphere, obviously, and then the right hemisphere back here in your occipital lobe. So just to be explicit here, the visual cortex is occipital, right? Auditory cortex, we know, is temporal lobe. Again, you've got that on both the left side and the right side. So the auditory cortex, to be even more specific geographically here in the brain, is sitting there. You'd have a mirror image, bluish, purplish area on the right side if we could spin this around and see that there. Speaking of spinning this around, there is an app called 3D Brain on both Android and iOS devices. That's awesome. I'm going to mention it again on Tuesday. If you want to get your hands on that, it's free. You can look at major parts of the brain and sort of see the brain in rotation. It's really, really good and can be really helpful for this segment of the course. We're not even going to talk at all, Hannah, about multiple personality disorder because you're more likely to get hit by an asteroid than see someone who has multiple personality disorder. It's got a crazy low base rate. I don't think it has anything to do with frontal lobe. Yeah, the app is called 3D Brain. Take a look at that, especially if you want to get different ways of sort of spinning this around and taking a look at it in 3 dimensions. It's really, really good. All right, I want to finish up in the last 5 minutes with one more polling question. But before I get to that, I want to just mention here Wernicke's area and Broca's area. We mentioned Wernicke's area earlier when we looked at the postmortem brain specimen way back at the beginning this morning. Right, we talked about this as the part of the brain that's involved with language comprehension. So you've been putting your Wernicke's area to a lot of work this morning, listening to me yammer on for almost 70 minutes now, right? Language comprehension. So that makes sense. This is the area that's related to hearing things, the auditory cortex. Wernicke's area sits here at the back, top rear part of the temporal lobe. So Wernicke's area is in the temporal lobe. Broca's area over here is involved. I got to get rid of my scribbling from the previous slide. Broca's area here sits adjacent to the motor strip. Remember, this motor strip sits right, why can't I get it to do what I wanted to do? Right along here is that motor strip. Well, this area now called Broca's area sits right next to it, and it is going to be the language production center, which actually makes a lot of sense, right? This is about language production. This is what I've been overworking since 8 o'clock this morning, producing lots of speech. And logically, geographically in your brain, it kind of makes sense to put the language production center right next to this strip that's about moving things, right? Because speech production is really about moving things, your mouth and your lips and your tongue and your vocal cords to produce those sounds, okay? So we will come back to this later on in the course when we take a look at language development, and we'll talk about 2 forms of aphasia, right? Because you can imagine what could happen here if you were to damage, let's say, Broca's area. So if you had damage to Broca's area, what do you think is going to happen? What are you going to be unable to do? Produce speech, okay? If your Wernicke's area was still intact, the wild thing is if this is still okay, you could actually comprehend what people are saying to you, but not respond to them. Or we could have the reverse. You damage this, and this is okay. So now, what's going on? I don't understand what you asked me, but I've got the ability to respond anyway. And you could potentially respond with written language. This would all be, something like a stroke or some kind of significant head injury. It would really depend on the localization of the damage via that stroke or head injury, right? So depending on the specifics, you'll get different patterns of deficits in people as a function of that underlying damage in the brain, okay? All right. Let me give you one final polling question because I know you guys love these, and this is the one that I usually turn right around and ask you as the first question when we get back together on Tuesday, face to face, okay? A laboratory cat could be made to twitch its whiskers by direct stimulation of which lobe of the cortex? I don't even need to give you the answer choices, but I will. Temporal, frontal, parietal, or occipital. Tell me which one and why. So if you think it's frontal, tell me why. If you think it's parietal, tell me why. Kristen's saying it's B because of movement. It's movement-based, says Hannah. Alexa as well, frontal because it controls movement. You guys got it, right? That many people can't be wrong, can they? Frontal lobe, because the frontal lobe, oh, that's good. I do blue on blue. That'll be really very visible. Let's try again. How about green, or light green here on blue? There you go. Frontal lobe. This is what happens in the last 5 minutes. I just lose brain power. So the frontal lobe is about movement. If I make the cat twitch its whiskers, that means I'm making it move its whiskers. That's going to be frontal lobe, that strip at the back of the frontal lobe called the primary motor cortex. Whew. That's what I've got for you guys this morning on tools of the neuroscientist and major parts of the brain. So let me clear out what I've scribbled here and try to exit out of that show mode and jump back here to our overview slide. So what we've done pretty nicely this morning is taken care of the major tools of neuroscientists. We'll finish up with the major parts of the brain on Tuesday. By the end, we'll get to zoom into the cellular level. We'll be taking a look at the neuron as kind of the building block of our central nervous system. So one of the last slides, if not the very last slide on Tuesday, face-to-face, will be this one on the structure of the neuron. We make a couple of other announcements. Your first set of learning curve quizzes are due on Sunday night at 11 on chapter 1. That was the introductory material plus research methods. 10 really easy points if you will just sit down and do what you need to do there. The other thing that I want to show you guys is the calendar here, not that calendar, this calendar for supplemental instruction. I would start going now because we're 12 days away from test number 1. That would give you the rest of this week, the full week next week, and even on Monday before the test to take use of, to make use of this incredible resource and service to help you do better in this course. Again, people who are going to SI are passing the course at a rate of 2 to 3 times better than people who are not going. Okay, so definitely do it. All right. 40 questions, and the Scantron information is in the syllabus. Yep. All right. Final questions before we wrap up. You can go in that order if you want to and go major parts and then zoom in and read it in reverse order, or you can read it the way they have it. It's up to you. I think it might make it a little bit easier to go to the major parts of the brain stuff that we've been talking about today first, because that's been our approach here. Okay? Any other final questions? I do have online office hours starting at 11, so let's wrap up here and have a good weekend. I'll see you guys face-to-face again in AL 201 on Tuesday. All right, guys. See you later.